Let's begin the test bank problems with the 2004 exam. So we have this circuit. We're going to close the switch at time equals 0, and we're going to calculate various things across this circuit. So we want to determine the voltage across the resistor R2 immediately after the switch is closed. So for part A, let's actually redraw the circuit at time equals 0 with the switch closed. So I have R2 right here. I have R1 here. And we have just an R2 label here. R1 is 15 kiloohms. And let me just shrink that a little bit. 15 kiloohms. Perfect. And we have a 20 volt battery here. Then at the end here, we're going to have I'm going to draw it in as a dotted line, the capacitor. The reason I draw it in as a dotted line, and it is a 20 microfarad capacitor, but more importantly, at time equals 0, this capacitor is going to behave just like a wire. So here's what that means for us. At t equals 0, when we trace the current through the battery, starting at the battery, it starts at the 20 volt battery. It goes through R2. Now here's the thing. It could go down R1, which has a resistance, or it could go through this 20 microfarad capacitor, which at time equals 0 behaves like a wire. It will completely circumvent this resistor and go straight through the wire that offers no resistance. Another way to say this is you have a 0 ohm resistor in parallel with the 15 kiloohm. The net resistance is 0 because this branch takes all of the current. So what that tells us is that there's no volts across this resistor because there's no volts through this wire. They're in parallel. All of the voltage gets consumed by R2. So it actually turns out that V across R2 in part A is going to be 20 volts. Now, for part B, we want to know what is the voltage across R2 a long time after the switch has been closed. So what we're going to do is we're going to go ahead and redraw our circuit. Once again, we have the 20 volt battery. We're going to draw R2. We will draw R1. And now, let's be clear. Again, we'll draw the capacitor here as a dotted line. But here we're going to be clear that in this case, at time equals infinity, the capacitor really acts like a brake as far as flow of charge is concerned. Now it has 20 microfarads on it. Sorry, it has a capacitance of 20 microfarads. We're going to figure out the voltage across it in a second, because that's going to help us calculate a couple things. In part B, we want to know the voltage across the resistor a long time after the switch is closed. So let's be clear. Now what's going to happen is we have the current flowing this way around the circuit. We have 20 volts on the battery. And let's be careful. We go around this loop here. None of the current can go through here because this is a break in the circuit. We did that exercise in class of looking at where circuits don't have any ability to have current go through them. And this branch right here has no current through it whatsoever. So when we write down Kirchhoff's voltage law, we have 20 volts minus the voltage across R2 minus the voltage across R1, that's this one here, equals 0. Now, although this capacitor from the perspective of current behaves like a brake, it still has voltage across it. Let's go to the graph and figure out what that voltage is. So we see here that the voltage at time equals infinity is 12 volts. So what I can say is that this capacitor has 12 volts across it. So this is from the graph. The next conclusion I reach is that this 15 kiloohm resistor is in parallel with this capacitor. Because it is in parallel, it also has 12 volts. I'm just making a note that it has 12 volts on it because it is in parallel with the capacitor. So now what can we say? We can now plug in some numbers to get the voltage across R2. So that will be 20 minus V2 minus the 12 volts on V1 equals 0. So the voltage across R2 is going to be 8 volts. Now, we want to calculate the value of resistor R2. Let's go ahead and do that in part C. So here's what we know. We know that there is 20 volts total in the circuit. We also know the current through R2 equals the current through R1 because they're in series. What else can we say? We know the voltage across resistor 2 is 8 volts. We know the voltage across resistor 1 is 12 volts. So let's go ahead and get I1 using V1 over R1. So that's going to be 12 volts divided by 15,000 ohms. Remember, a kilo ohm is 1,000. So when we actually calculate that out, we're getting 0.0008 amps, or you might want to write that as 0.8 milliamps. But that's not the question we want to answer. We want to know the value of resistor 2. So we also know that I2 equals I1, which also equals this 0.0008 amps. And now we can say R2 equals V2 over I2, which is going to be 8 volts over 0.0008 amps. And that's giving me a 10,000 ohm resistor. So, just to kind of get clear, this is the answer to part A, the answer to part B, and the answer to part C. Now it says, calculate the energy stored in the capacitor a long time after the switch is closed. Let's see. I'll just use the formula 1/2 CV squared. And so that's going to be 1/2. Now, the capacitance is 20 microfarads. That's 20 times 10 to the negative 6th times V squared, which is 12 squared, which is 144. And so when I work all that out, so that's 20 times 10 to the negative 6th times 1/2 times 12 squared. I'm getting 0.00144 joules worth of energy. Now we move on to part E. It says on the axes below, graph the current in R2 as a function from 0 to 15 seconds. So let's go ahead and actually start. So at time equals 0, we know that there are 20 volts across R2. So let's just kind of do a little label here. So at time equals 0, V2 equals 20. So what that means is that I2 is going to equal 20 divided by 10,000. And when we actually work that out, I'm going to actually do this in milliamps. So that'll be 20 divided by 10,000. And that gives me 2 milliamps of current. And at time equals infinity, I2 ended up being the same as I1, which again, was 0.8 milliamps, to be absolutely clear here. Let me make absolutely sure I have that right. So 20 divided by 25,000. Yep, okay. So at time equals infinity, I have 0.8 milliamps. So kind of looking at this graph here, let's be really careful. It's right around the 7-minute mark that we reach that limit of 12 volts on the capacitor, which tells us that that's when we're at the effective infinity of time passing. So right here at 7 seconds, I can actually, let me just go ahead and label this. So I'll say that this is 1.0 milliamps here and 2.0 milliamps here. So that means we've got, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So right here is 0.8 milliamps. And right at 7 seconds, we can go ahead and just kind of draw that there. At time equals 0, we're starting at 2 milliamps here. And let's just kind of go and see how the capacitor mimics this. So one thing is that at now we can actually use a couple points on the capacitor to guide our current graph. And here's what I mean. Here we have a capacitor voltage at about 1 second. We've got about 6 volts on the capacitor. So that means we've got 6 volts across this resistor. And let's be clear then that the voltage across R2 is going to be 14 volts at time equals 1 second. So at time equals 1 second, voltage across resistor 2, is going to be 14 volts. So that means the I across it is going to be 1.4 milliamps. So at 1 second, wait, 1, 2, 3, 4. So at 1 millisecond, we're going to have, if this is 2 milliamps right here, this is 1.5, 1.4 volts at 1 second. Okay? So we've got 1.4 milliamps at 1 second. Let's go back to this graph here. Next, at 2 seconds, we've got about 8 volts on the capacitor, which means we have 8 volts on R2, which means, let me say that one more time. At time equals 2 seconds, we've got 8 volts on the capacitor. That means we have 8 volts on R1. That means we have 12 volts on R2 by Kirchhoff's law because it has to add up to 20. So what that tells us is that if we have 12 volts on R2, that means at 2 seconds, we're going to have 1.2 milliamps on it. Continuing. At 3 seconds, we've got about 10 volts on R1. That means we have 10 volts on R2 to add up to 20, which gives us 10 milliamps of current at about 3 seconds. Whoops. At 4 seconds, we have about 11, so that means we've got about 1.1 milliamps right here. 9 milliamps right here. And so on and so forth. So I can actually kind of draw a little trend here just to get that right there. So that, let me try that one more time. So we draw the curve through this line using Kirchhoff's laws to get that graph as tight and precise as possible. There we go. Close enough. All right, so that is how we actually draw the graph here. Again, we use Kirchhoff's laws at various points to get the voltage through the resistor at various points and therefore the current. Now it says indicate below the energy stored in the capacitor is less and greater than the same as it was with resistor R2 in the circuit. So what we're going to do is we're going to remove R2 and replace it with another resistor of lesser resistance. So let's go ahead and figure that out. So here's an extreme case. Sorry, I keep turning to the wrong problem. Let's make R2 equal to 1,000 ohms. So if we make R2 equal to 1,000 ohms, what's going to end up happening here is that at time equals infinity, we're going to have a current let's just see. So the total resistance is going to be smaller. So total resistance is going to be smaller if R2 is smaller. So I through R1 is bigger. That implies V1 is bigger, which implies VC, which is equal to V1 is bigger. So it's going to be an energy 1/2 CV old squared versus 1/2 CV new squared. And since V new is bigger than V old, the energy is going to be greater than. All right, so that is question number 1 from the test bank.